Well, hello. Welcome back to IAC 101. I'm Dr. Mike Muller. And in this episode, we're going to focus on energy efficiency in industrial cooling systems. Although there are several other systems to choose from, we chose industrial cooling because there's a big need out there for understanding how industrial cooling works. To be honest, people just don't understand chillers and chiller systems for that matter. And that's why we're dedicating the next two episodes to reviewing these cooling components. So what needs cooling in a factory? Well, both people and processes need cooling, and we tend to keep people cool with air conditioning. While this is very important, we're not going to consider it here. We're going to consider it in a later episode on space conditioning. So currently, we're going to focus on process cooling. This includes a whole variety of operations such as process temperature control, quenching, cooling molds after manufacturing, and managing chemical reactions. We're also going to focus on ancillary processes which need temperature control, such as refrigeration, freezing, and cold storage. We made stuff, now we have to keep it cool. Other times, cooling is necessary simply to control the humidity in a particular place. And remember that computers these days generate a huge amount of BTUs that must be removed. So equipment cooling with an emphasis on data centers is something that should be explored. The reason we pay attention to industrial cooling is that cooling systems are the least understood even by assessment teams visiting factories. People seem to think they're magic machines that make chilled water by some process we don't fully understand. But if we ignore it, we'll miss some of the most important opportunities for energy savings, especially in an electricity-only plant. Sometimes in electricity-only plants, we struggle to find big savings, and that's where I would recommend focusing on industrial cooling. Now, counterintuitively, we don't generally cool at the same place where the cooling is needed. We find that in most factories, industrial cooling will be indirect, meaning we cool something first, most often a chilled water loop, and then we circulate that water throughout the plant and use heat exchangers to cool whatever processes actually need to be cooled. Now let's start with chillers. To understand how they work, we need to go back 150 years and see how we used to cool things then. And the answer is an ice box. I'm old enough to remember one at my family's summer place. Ice would be harvested from a previous winter or from an ice house, and you would stick it in this one compartment, and then you would hope that it would keep other things like your milk, vegetables, and uncooked meats cooled. Well, this didn't work all that great, and by the end of the summer, you were out of ice, and what were you going to do? So we developed a device which required us to understand some fundamental physics. These 2 points are key, so we cannot say them enough. First, if you have a gas and you compress it, its temperature goes up. So if I raise the temperature of a gas above room temperature, heat will transfer out of that gas. Secondly, if we have a liquid that evaporates, now it's gone from a liquid state to a vapor state. And what we find is that the temperature must drop unless we have energy coming in to cause that phase change from somewhere else. So evaporating room temperature liquid creates a cold gas, and we generally do this by suddenly dropping the pressure of the liquid. And that's it. If we understand that physics, we can understand all of the chillers that are made today. Here's an image that shows the most common way this particular physics is applied. It's called a vapor compression refrigeration system. In this cycle, we have a refrigerant fluid that we put inside, such as freons or any other refrigerants that function similarly. If we look at this, you see we start with a compressor. The compressor raises the pressure of the refrigerant, and from physics, we know the raised pressure results in a higher temperature. So vapor is sucked in and then sent out at a much higher temperature from the compressor. From there, it goes to the condenser. A condenser is a device which is generally found outdoors. Its primary job is to cool that now hot gas until it changes phase into a liquid. To do this, we're going to use gravity. The fluid comes in as a vapor up at the top, and as it cools, it starts changing phase. The liquid will be heavier, so when we get to the bottom, what we're going to be dealing with is entirely liquid. Note that we don't need to have any fancy device for separating liquid from gas because we rely on our good friend gravity. So to recap, we had a compressor which compressed the gas and made it very hot. And then we went into the condenser which changed that gas back into a liquid. Now, as seen in the picture, we're going to go through a valve. This valve drops the pressure dramatically, causing some of the liquid to evaporate and greatly reducing the temperature. Now we have a cold material which we can put into our evaporator. As the evaporator changes all the liquid into vapor, it will suck energy in from the environment because it's now colder than its surroundings. And here we use gravity again to our advantage. If we have some combination of liquid and vapor together and we want it to come out just vapor, then we come in at the bottom with the liquid. As the flow goes through the evaporator, the vapor will travel to the top and let gravity separate it from the liquid, thus allowing it to leave the evaporator with 100% vapor that's ready to go back to the compressor. If you look at the cycle and ask the question, where am I spending money? There is only one place. The only component where money is spent is the compressor. The other operational components don't have any operational costs. Note that if you look at a different kind of cycle called an absorption refrigeration cycle, we can replace that compressor, and that's going to save us some money, and we're going to view that in the next episode. So how do we think about efficiency for this cycle? Efficiency is not looked at in the same way you would look at for, let's say, a motor system. That is, the work you're getting out of it over what you have to pay for, what you put in. Instead, we're looking at how much heat you can pull out of a refrigerated space over how much it costs to drive the compressor. This ratio is termed the coefficient of performance, the COP, the amount of useful cooling divided by the energy usage of the compressor. So what are typical numbers? Well, there's a wide range of COPs, coefficients of performance, for chillers in operation. On this chart, you can see a value as high as 5 and as low as 2.5. And this is one of the reasons we need to consider upgrading aging chillers. Now, it's a tough sell with industry because chillers are expensive. However, if you can show that the efficiency is down to a coefficient of performance of 2.5, and you can double that with an upgraded system, you're going to pay that new chiller off pretty quickly. The reason plants are unaware of the COPs of their chillers is because the measurement of COP requires knowing flow rate. It seems simple, but this is not. Okay, remember the purpose of a chiller is to pull energy from a cooled space. It came into our system, and now we need to reject it somewhere back into the atmosphere. We've got to do something with it. And there are two classic ways to do this. First, you could have a radiator, just like a car radiator attached to the condenser of an air-cooled type chiller system. Another option is to transfer heat from the chiller, now this hot stuff, into a new loop which flows out to a cooling tower where the energy is discharged into the atmosphere. The most common method is the second, a water-cooled chiller system. And there's a very important reason for this. Not only do we cool with water effectively, but we're able to lower the temperature more than we could with ambient air by using the physics of evaporative cooling. In a cooling tower, the evaporating water takes out enough energy so the actual temperature can drop below the ambient outdoor temperature. Amazing, right? And it's done, okay? A reasonable question to ask, isn't there an extra complication to adding a cooling tower to a chilled water system? Adding another cooling loop and the electricity for the fans and pumps, etc.? So my standard answer to this question is to follow the money. If people are spending money for a solution, it's probably a good idea. Now I'm going to take you back. If you've watched the movie West Side Story, you may see it as a romantic retelling of Romeo and Juliet. Great singing and dancing. It did get Best Picture in 1961 after all. Unfortunately, I'm so messed up that what I noticed when watching the film was in the opening credits, before you see the gang start dancing, you fly over the city, and in 1961, most of the tops of the buildings have these telltale fans of cooling towers on the roof. In 1961, it was standard operating procedure to have a cooling tower in chilled water systems, and that has not changed until up until today for any good reason. Now, looking at the water-cooled device itself, the chiller, you'll notice two very long tubes. These are shell and tube heat exchangers. The lower one will usually be the evaporator, and the next one up will be the condenser. Now, the compressor usually sits on top so that any heat rising from the compressor doesn't get absorbed into the evaporator. That wouldn't be good. Shell and tube heat exchangers are very good for phase change. And what you know from our previous slides here is that there are phase changes in both the condenser and the evaporator. Now, in some cases, either because of space constraints or some retrofit applications like a computer system, you may not put in a wet cooling tower, but rather a self-contained air-cooled chiller, such as the one shown here. This could be done in case water is expensive, limited, or more likely unclean. With unclean water, you may find using an evaporative cooling tower where the water evaporates, but the junk that's in the water doesn't, can be very expensive to manage. And so your water management fees outweigh any savings you get from a chilled cooling tower, a cooling tower system. So we see a reasonable number of air-cooled chillers, especially more since computer rooms and data centers have shown up in a lot of places. And I will say, especially in California, where not only water is scarce, but it is coming from the aquifers is often loaded with stuff you don't want. However, there's no question from an efficiency perspective, a water-cooled chiller is a much better plan. So now we understand a little bit about how the chilled water system works. Let's move on to evaluating the low-hanging fruit, those easiest measures to implement for industrial cooling improvements. The first is obviously to contain the cold. This cold water you are passing through your plant in your chilled water loop is going to find a lot of heat, which your industrial plant is probably producing. So you want to separate the cold from hot by using effective insulation. The problem is usually not long runs of pipes. They're often well insulated, but the joints and valves at the end of these long runs are often left uninsulated. And this is something to pay attention to if you're doing a chilled water assessment. Removable Velcro type insulating covers are cheap and sized for all kinds of elbows, joints, and valves. It's also important to note that uninsulated chilled water pipes can cause condensation to form from the air in the room. Now, if the chilled water temperature is below the dew point of the air, and for chilled water, it's going to be in the 40s Fahrenheit, you would expect there to be condensation if you don't insulate. But here's something that's not obvious. If any of the condensation seeps into an existing insulation, it makes it worse than no insulation at all. Wet insulation causes the piping to act as if it were bigger, losing more energy and causing the water temperature to increase. You'll also have the problem of mold forming and possibly rust on steel pipes. So during an assessment, you can walk along the piping looking for leaks and feel if there is any water being held by the insulation. It'll be spongy. Another thing to remember is that the condensation problem is going to work against us in terms of vertical piping. In the picture, several joints are not insulated, and although there is minimal pipe uninsulated, the condensation will occur and will run down because of gravity into the insulation and compromise it. A place where we don't love gravity. Besides insulation, another common thing to look for is opportunities to keeping cold spaces separate from warmer ones by using doors, flaps, air curtains, and walls. You might see a quenching tank using chilled water which is open to the air, and this can be handled either with a removable lid or in some cases with floating plastic balls, which easily move out of the way when you dunk something into the tank. Next, let's look at another important topic, strategies associated with operating multiple chillers to meet a cooling load. So let's remember that when you size a chiller, you have to size it for the worst case scenario, the hottest August afternoon. If your chillers can't manage when it's at its worst, you're going to have to shut the plant down. Nobody can tolerate that. So generally your chillers are oversized for their normal operation. Here is a diagram below showing the percent of time a single chiller is at a particular load over 6,500 operations. You can see that it's at 50% load about 19% of the time. And then as you start going below 50% load, you see you've got 15%, 13, 12, and 11 respectively as the load gets less. So you've got more than half of its operation. This is a chiller just taking some data off the internet, which is operating at 50% load or less more of the time. Is this a problem? Well, we need to look at the actual performance and see if there's a problem of operating chillers at low load. So in this next figure, we see a performance curve for a typical chiller plotted as load versus kilowatt per ton. Now, the unit of tons of cooling is an old one dating back to ice houses and represents the energy needed to melt a ton of ice. It is easily changed into something more relatable, and 1 ton of refrigeration is actually 12,000 BTUs per hour. Anyone using kilowatts per ton to measure chillers' performance has to recognize it's inverted from the coefficient of performance. So whereas you want a high coefficient of performance, you're going to want a low kilowatt per ton, okay? So again, in this figure, you see the actual data for a 228-ton chiller. So about 120 tons is about half loaded. And you can see as we go down below half loaded, your performance drops dramatically. So generally for offloaded chillers, operating anything below 50% is not a good idea. So to mitigate the effects of offload performance, we propose the idea of having multiple chillers, but having them of different sizes. According to industry surveyed, about 80% of industrial plants with chilled water systems have more than one chiller. So they understand how to do that. That's the good news. But the bad news is if you don't run them correctly, you may not be able to help anything. A case study in California demonstrated 5% of savings, 5% in savings in chiller costs when two 200-ton chillers, both 45% loaded, were modified to have one turned off and the other run at about 90% load, contributing to about a $2,800 per year savings. No implementation costs. This is just an operational change in how you do things. So we want multiple chillers, but we want those chillers operating intelligently. And those are things we look at carefully when we're doing an assessment. So it'd be great if we could determine the loading of various chillers and understanding whether they're being operated intelligently or not. And that turns out to be a little tougher than we would hope. For newer chillers, you can read the load right off their digital displays, which you can look at even while they're operating. You also can hook up a power meter and a data logger for either a new or an older chiller, but unfortunately to hook them up, you often have to shut the chiller down, and management may not be too cool to do that. Pun intended. A caution here that COP, or kilowatts per ton, is more difficult to measure than power consumed. Energy in, the kilowatt hours going into your chiller, that's easy. But the cooling effect in a chilled water loop or the energy rejected in a cooling tower both need two things. They need the temperature differences. They also need the flow rates. And the latter is the tough thing to measure. So estimates can be made using pump curves for the chilled water distribution system or for the pumps taking water to the cooling towers. And you'll say, okay, based on their RPM, we'll get a certain flow rate. And if they both agree, then you can get a reasonable estimate, a reasonable feel for the COP. Otherwise, we have to end up trusting chiller documentation to determine the COP as a function of load. This brings us to the end of this episode. Time to take a break. In our next episode, we'll look at further into other topics like free cooling, floating heads, thermal energy storage, and stuff like that. Thank you for watching. I'm Mike Muller. See you next time.